Hi everybody, so we're going to finish up the last concept to deal with fluid drag, and that's centered around the idea or a concept called Reynolds number. So if you recall in class, we talked about there's two different types of drag. There is inertial drag and then there is viscous drag. And depending on the situation, one usually dominates over the other. There is a gray area where they both contribute. So a simple way, even if it's a little bit rough, the way to determine whether you are going to use inertial drag or viscous drag is to look at something called Reynolds number. So there is an equation that goes with it. It's already given. I'm going to do a quick little derivation. It's fairly simple. And then we'll talk about conceptual situations, do an example, and then I'll link a video for you to watch to show how it especially is important for when you're trying to propel yourself through a fluid, especially water, especially living things, large or microscopic. Even applies to swimmers or boats, etc. So Reynolds number is simply defined as the ratio of inertial drag to viscous drag. And like I said, there's an equation where the Reynolds number, RE, equals the velocity of the fluid flow, or the object that's flowing, because it's relative, the size of it as measured by its radius, and we're going to probably treat something like a sphere. The density, and I got to be careful here, it's the density of the fluid, not the object, and then its viscosity. Okay, so where does this equation come from? Well, it simply comes from the definition, right? So if RE is inertial fluid drag divided by viscous fluid drag, then we have CD, that's the coefficient of drag based on that. And this is going back from previous notes, the previous page, R squared, V squared. And then for the viscous drag, we have 6 pi, right, eta RV. So we see that the V squared and V cancels out, R squared and R cancels out. And then the coefficient of drag is a number, and we're going to cancel it out with this 6 pi. We're going to assume the same. So what we're left with is the rho fluid, R, V, and the eta, as we see here. And note that Reynolds number is a number. It's dimensionless. We can prove to ourselves that these work out. That's actually a good problem for you to do, but we don't need to do it here. Okay, so what can we learn if we have a Reynolds number? Okay, so we can get a rough idea of whether we should expect laminar flow or turbulent flow, let's say in a pipe, let's say in your house or any building. So the general idea is if the Reynolds number is less than around 1,000, then you're going to have laminar flow. Okay, so the slow Reynolds number usually means nice smooth flow, and that's because it corresponds to a low speed. In other words, if you have a fluid moving really, really fast, the V part in here is going to inflate your Reynolds number because density of the fluid is a given. The size of the pipe is, can be changed, but not radically different. Eta is given for water, so what you can control is the speed. And a big speed usually leads to a high Reynolds number, which will lead to more turbulence. Now, for turbulent flow, you might think it's as simple as greater than 1,000. Actually, no, it's greater than, depending on the situation. I'm going to go here with about 2,000 value. Okay, and so you might ask, what happens between 1,000 and 2,000? You have a mix or mixed flow. Okay, where it's kind of a gray area. All right, another aspect of looking at Reynolds number, okay, different than whether you have laminar and turbulent, is which type of drag dominates. So a low Reynolds number, it's going to be viscous drag that dominates, which kind of makes sense, because if we look at the definition where viscous drag is on the bottom, if it's a big value, then Reynolds number is going to be relatively small, and so we know to use the viscous drag equation. And what's important in terms of things they're trying to move through a fluid like water, it usually corresponds then to a tiny object. Sorry, I'm not meaning to cross it out, that's to underline it. Okay, because a tiny object in the numerator of the Reynolds number equation is going to give you a small number and or a high viscosity. Okay, In other words, if something's trying to swim through honey or molasses or even oil, which would be high viscosity, it's viscous drag that's going to dominate because that, if you will, stickiness. So that would make sense at high Reynolds number, inertial drag is going to dominate. And that might be because you have a very large object trying to move through it. Think of a whale or even a human swimming through water. Or you have a dense fluid. Okay, so we can do a simple problem. We have oil, it has a viscosity of 0.35 Pascal seconds, density, etc., etc. Determine if the flow is laminar or turbulent. So if we use the Reynolds number equation, right, which is VR rho of the fluid divided by eta, we can plug in a number. It's pretty straightforward. I'm not putting them in any particular order. Maybe I am. Okay, 0.35. And if we punch that out, we get 1190. So let's just call it about 1200. And again, it's dimensionless. So, well, we're going to say, is it laminar or is it turbulent? I would lean towards laminar. It is in that kind of gray area, but we have laminar flow. And because the Reynolds number is kind of low, we're going to expect viscous drag to dominate, which means that if you're going to swim through it, you're going to be a really small. In other words, if you're going to propel yourself in the fluid, you're going to rely on viscous drag to allow you to propel yourself rather than inertial drag. And in that light, that last statement I just made, okay, I'm going to attach to this tutorial, I'm not going to play it now, a neat little, I don't know, 5 or so minute video that looks at how Reynolds number affects how big objects and small objects move through a fluid.